welcome to our video. Today we will be teaching you a couple of ways to find the area under a curve. The first technique for finding the area under the curve that we're going to talk about is something called sigma notation. This is the Greek letter sigma. The sigma symbol is the Greek letter S, and in math is often used as a compact way to symbolize sums and is also called the summation notation. But what is the equation to find area under a curve using summation notation? It's sigma times f of x sub k times delta x. And delta x stands for your width, where your f of x stands for your height. Here's a graph of the equation y equals 2 to the x. As you can see, the shaded area is broken up into 5 equal sections, each section with a base area of 0.4. By using this x sub number notation, you can represent your base distances starting at 2 and ending at 4. Because the bases of your rectangles are 0.4, you're going to count up from 0.4, 2.4, 2.8, etc., all the way to 4. This is what that should look like when you're done. For the equation, you're going to use that same form that we looked at earlier. Because you had 5 steps in the x sub 0 before, you will go with your sigma k equals 0 with a 4 on the top. This is because you don't want to overpass 4, which is your top number, which is x sub 5. You only want to go up. Then your original equation is 2 to the x, so you should do 2 to your new equation, which is 0.4k plus 2. Lastly, the most important is adding in your delta x, or your base, which is 0.4. Now run that through your summation program on your calculator, and you should get that the area equals about 15. Great job! Now we'll show you how to find the area under the curve using left endpoint rectangles. A left endpoint rectangle is a rectangle under the curve when the rectangle's left corner is touching the curve. When solving a problem with left endpoint rectangles, you will be given a domain showing the x value where the first rectangle begins and the x value where the last rectangle ends. The number of rectangles to make in that area will also be shown. To make our graph, we first need to know what to count the x values by, or in other words, how wide to make each rectangle. To do this, we have to take the highest x value in the domain, subtract it by the lowest x value in the domain, then divide the sum by however many rectangles the problem said to make. Once this is done, you can start making your graph. For our purposes, the exact slope of the line doesn't really matter, so since the curve we're drawing is for an exponential function, we'll just draw the general shape of that function. At this point, we need to put our x values on the graph. The problem told us our lowest and highest x values, and we figured out that the x values go up by 0.4 each time. Therefore, we know that our first x value is 1, and that our second is 1.4, then 1.8, 2.2, 2.6, and 3. We will also use subscript notation to label the x values. X subscript 0 is always the first x value given, so in this case that would be 1. Now we just have to draw the rectangles. Since our first x value is 1, that's where the left side of the first rectangle will be. The second rectangle will start at 1.4, and so on. So now that our graph is made, let's go back to our equation for the approximate area under the curve and add in what we've already found. For our indices, we will use the subscript x's that we labeled on our graph. The lowest subscript x that corresponds with the left endpoint, one of our rectangles, is x subscript 0. The highest is x subscript 4, so those will be our lower and upper indices. We've also found our change in x, or in other words, the width of each rectangle, so let's plug that in too. There are 0.4 units between each of our x values, therefore our change in x is 0.4. All that's left to do now is create our equation for finding the height of each rectangle. To do this, we're going to plug in 0.4 as the x variable. And since our first x value, x subscript 0, is 1, we will add that to the k variable as well. Make sure that 0.4k plus 1 is in parentheses. Okay, so now we've finished writing our equation. If you plug this into your sum program on your calculator, you should get the estimated area, which is 752 units squared. This is an underestimation of the area because the left endpoint rectangles don't fill in all the area beneath the curve. Let's move on to right endpoint rectangles. Right endpoint rectangles are rectangles under a curve when the rectangle's right corner is touching the curve. Solving for estimated area using right endpoint rectangles is the same process as when you're solving with left endpoint. The only difference is that for the indices, the upper bound and lower bound are both 1 higher than when using left endpoint rectangles. The reason for this is that x subscript 1, rather than x subscript 0, is where the first right endpoint touches the curve. This is different from the left endpoints, where the first endpoint touches the curve at x subscript 0. If you plug the same equation into your sum program with the new indices, you should get 992 units squared, which is an overestimation of the area. The last way that we are going to tell you about for finding the area under the curve is by using trapezoids. This is the equation you use to find the area of a trapezoid. In this first trapezoid, this will be your B1, this will be your B2, and this bottom section will be your height. If you take those values and plug them into your equation, it should look something like this. Half 5 plus 2 times height, which is going to be 1. That equals 3.5. Now repeat those steps for every trapezoid and then add those together for your trapezoidal area. Devonte rode their bike for 30 minutes at 2 miles per hour. Once they reached the bridge, they sped up at a constant rate for 30 minutes until they reached 7 miles per hour after 1 hour and 30 minutes. At the 2-hour mark, Devonte suddenly declined their speed to 4 miles per hour. They continued at that speed for 30 minutes and then gradually declined back to 2 miles per hour after another 45 minutes. You can see that represented in this graph. But when you find your area under the curve, what unit will it be represented in? It will be represented in miles. Miles per hour is miles over hour. And then, when you multiply that by your time, which is on the x-axis, you're left with only